Okay, now let us see the example number 6 about software interrupt. In this example, we will see how software interrupt is used as a part of the main program. If you see the exceptions of the ARM processors, we have already seen fast interrupt request. Now we will see software interrupt. The mode of operation for software interrupt and reset is in supervisory mode. Whenever a exception is received, as we know, there is a interrupt vector table which has the address of the interrupt service routine. So fixed offset for each type of exception, and these addresses contain instructions of one of the following form. That means whenever a exception is generated, it will go to a fixed interrupt vector location where there will be either branch and address instruction may be there, or LDR PC comma offset value will be there, or move PC comma immediate value will be there. So in any one of these three forms, the program counter will be loaded with the physical address of the ISR, interrupt service routine. Whenever exception occurs, exception causes first of all mode change. As we have seen, depends on whether it's a fast interrupt or interrupt request or reset or software interrupt, the mode will change. And after that saves the CPSR, current program status register, to the SPSR of the exception mode, and saves the program counter contents to the link register of the exception mode, and sets the CPSR to the exception mode, and sets the program counter to the address of the interrupt service routine. Okay, so while entering into the exception, that is the interrupt service routine, it will verify whether the exception uh, state is ARM state or whether it is a thumb state, because as we know that it depends whether it, in case of a ARM state, it copies the address of the next instruction into the LR, and in case of a thumb state, it is a 16-bit mode. So it has to see in which state it is in. The exception handler does not have to determine the state when entering an exception. Okay, so and copies the CPSR into the appropriate SPSR, forces the CPSR mode bits to value which depends on the exception. So the software interrupt instruction generates an exception, forces the processor into supervisory mode. So this is one way or indirect way of switching from the user mode to supervisory mode. So whenever user wish to access the supervisory calls, then he can execute software interrupt instruction. So whenever software instruction is executed, SWI instruction is executed, then the program counter will be loaded with 08, which is the offset address of the interrupt vector table. And software instruction also can contain conditional execution, means SWI instruction can also verify any condition to be verified, and if the condition is satisfied, then only that service routine will be executed. And the it is also possible to encode an integer into the unused portion of the software instruction. That means the instruction, along with the instruction, you can also specify some offset value so that you can have a number of software interrupts. Say for example, if you look at the format of the software interrupt, the first portion, bit number 28 to bit number 31, is the conditional code. Then the last portion, that is 0 to 23, is the offset value. So bits 0 to 23 are unused, and user can define numbers can be encoded into this space. And as we can see, the as far as the priority of these interrupts are concerned, the software interrupt has the 6th priority, and reset is the highest priority. And whenever the, as you can see, reset is interrupt is received, the I bit, interrupt request bit, and the FIQ, fast interrupt request bit, both the bits will be set. But however, in case of a software interrupt, it is a only interrupt request bit will be set. Okay, now let us see the programming example, how to write a program for the software interrupt. Go to project, open project. Now this time we are using the example number 6, that is the software interrupt. Okay, so in this example there are three sections we'll have to go through. One is about the main program, where you are initializing the interrupt, software interrupt, and there is a interrupt handler, so that whenever the software interrupt request is received, then the software handler, it will enter into the interrupt service routine. Then there is a piece of code is written in the interrupt service routine, which will take care of the context switching and saving the contents on the link register and so on. And the most important point is about the initialization of the hardware itself, that is the startup file, so that the interrupt vector table of the all the interrupts is taken care by the startup file. So in the main program, if you look at the main program, first in the main program we have defined some a pattern where whenever a software interrupt request is received, the LEDs, alternate LEDs will be on. So that pattern as a variable integer is defined. Then since the direction register of those LEDs has to be output port, so IO DIR1, that is GPIO1, bit number 16 to 23 bit is set, and initially the contents of the port is cleared. After that, there are two software interrupts, as you can see. One is SWI call 1 and SWI call 2, where two types of software interrupt service routines we want to call. In one case, we are actually passing the parameter pattern value. In the second case, there is no value which is passed. Okay, now whenever this uh, uh, the service routine is called as WA call, then it will pass the offset value, so that then the corresponding software interrupt service routine will be executed. As you can see, the syntax of SWI0 and the syntax of SWI1. So whenever it enters into this service routine, it will clear the contents of the port, and whatever is the value passed as a part of the service routine, that will be assigned to the set register. In the second software interrupt, it will clear the port, but it will pass alternate LEDs will be on, so that you will come to know whether it is because which software interrupt, whether it is a software interrupt 0 or software interrupt 1. And in the interrupt handler, the interrupt, whenever the software interrupt is received, first of all it will store the contents of R12 and in link register, so that the R12 can be used in the rest of the code, and it will get the contents of SPSR, and it will verify whether thumb bit is set or not, so that it has to take care of, in case of a thumb bit, the it has to load the half word, otherwise in case of a ARM mode it has to load the full word into the R12 register. Okay, then it will verify what is the SWI number, that is the offset value. Accordingly, it has to execute the corresponding service routine. Then once the address is been calculated, then then it will call the corresponding interrupt service routine. Okay, so now let us simulate the program. Okay, so in this, since we are using the peripheral, which is GPIO 1, let us view the contents of this. So now if I let us execute the program in single stepping fashion. So initially when you reset the microcontroller, as you can see, you are in the supervisory mode, and in CPSR also you can see the I flag and F flag both are set. So as a supervisory mode, the mode bit is 13, which is a hexa value. Now if we do the single stepping, right, initially the cursor is at the in the main function. If we do the single stepping, now as you can see, since the uh, startup file, it will enter into the startup file. So obviously first the starting of the program will be executed. So as you can see, as a startup file, that is initialization of the PLL and initialization of the peripheral clock. So all that code will be executed. Right, after that memory controller initialization is getting executed. Okay, now as you can see, the initialization of the various modes of operation. So set up the stack for each mode and enter, it will enter into various modes of operation. Say for example, at present the system is in the supervisory mode. Now if we execute single stepping, now we can see the undefined, right? Now you can see the undefined uh, function is being executed, which is where we have defined. Now after this, now it will enter into the abort mode. For example, at present in undefined mode, the moment if I execute this, then it will change the mode. This is in the abort mode. Now again I am changing the mode of operation. Now it will enter into the fast interrupt request. As you can see, now this time it is in the fast interrupt request. Again I am changing, now it will be in interrupt request mode. Now it will enter into the supervisory mode. The mode changing is being happening here, supervisory mode, right? So it is in the supervisory mode. So this is how so far for entire uh, stack being initialized for various modes of operation, so that as and when a exception happens, then that corresponding stack will be used in order to give the service to that service routine. Okay, now once this is done, as you can see, now it will enter into the main C code, because the initialization of the ARM processor is over. Now the moment if I execute this instruction, it will branch to R0, which is nothing but main program. Okay, now as you can see, now we are here where it comes back after hardware initialization, the main program. Now I am still in the user mode. Okay, now if I execute, oh, now see, it has changed the mode, because when you have entered the main program, it is in the user mode. But now since you have executed SWI instruction, then it has entered into the supervisory mode. And the contents of CPSR is 13H, which is the supervisory mode. Now as you can see, because you have executed a software interrupt, then the program counter will be loaded with the SWI address, that is the interrupt service routine of the software interrupt. Now see, since the software interrupt handler address is loaded in the program counter, automatically the program is switched to the ISR of the software interrupt handler, where the context restoration and the verifying the mode of operation and then loading the ISR routine of the corresponding SWI call will takes place in the SWI handler. As you can see, there is a difference in offset. In case of thumb it is 2 and in case of a arm it is 4. Okay, now it has entered into the, since it has calculated the offset value and it has loaded the program counter with the service routine of SWI0, where we have requested that particular software interrupt. Now in this, where as you can see, first we will clear this contents. Now you can see the bits, alternate bits are set. AA value is loaded into the GPIO register set bits. Now it will come back to the main handler, where the interrupt service routine has been serviced, and after that it has to load. That means it will have to retrieve the contents of the return address and will come back to the main program. Okay, now see, it will come back to the main program from where the interrupt request has been generated. Now this time we will be calling software interrupt again, but only difference is there will be a offset value, different offset value will be there. Okay, now since we have come back to the main program, we are in the user mode. If I execute this, now as you can see the mode is being changed. Now again and the supervisory mode. Now since the it has requested software interrupt, again program counter will be loaded with the SWI, that is a software interrupt handler address, which is stored in the interrupt vector table. Okay, now it has entered into the SWI handler service routine, where again the whole procedure will be repeated, except that this time the call SWI function will be second one. Okay, now as you can see, now it has entered into the second software interrupt. Okay, now alternate bits will be set here. Now if I execute this, it will come back to the interrupt handler from where it has called the function, and then once it will retrieve the return address, it will come back to the main program. Okay, now it is in the while loop, infinite loop. So that is how one can switch from the user mode to the supervisory mode by using the software interrupt. And you can have types of software interrupts where offset value can be part of the software interrupt itself, and these software interrupts also can be conditional. Let us look at the general purpose input output lines of LPC2148. LPC2148, when you reset the microcontroller, all the GPIO lines are act as a input output lines. They have 4 control registers to configure the input output lines: IO DIR, IO pin selection, IO set, and IO clear. This special function register like IO DIR, this register decides the direction of the GPIO pin. If this SFR is 0, that means that particular pin is input. If the bit is 1, that means that pin act as a output. You can use the logical operators to set or clear the bits, like IO 0 DIR or with 1, left shifted by 31 bits. Similarly, if you want to set the bit of the port, then you can use IO set, and if you want to clear the bit of the port, there is a IO clear special function register. So LPC2148 has two separate SFRs, one to set the bit, other is to clear the bit. Since every pin of the LPC2148 has multiple functions, like primary function is GPIO, otherwise there are alternate functions, first, second, third. So 4 possibilities are there as far as the pin functionality is concerned. Say for example, port 0.30 has 4 functions. One is, if it is 00, it acts as a general purpose input output line. If it is 01, then it acts as an analog to digital converter of channel 3. If it is 10, it acts as an external input 3. Otherwise, if it is 11, it is a capture, input capture for timer 0. So there are 3 SFRs are there for general purpose input output lines. Pin select 0 SFR takes care of 0.0 to 0.15 of port 0, and pin select 1 SFR takes care of pin number 0.16 to 0.31, and for port 1 the pin select 2 SFR will control bit number 16 to 31, which can be configured. Similarly, one can make use of the logical operators to set or clear the bits of the ports. In this case, in this example, 3 will be left shifted by 28 times and will be complemented and with pin select 1. Then 1 will be left shifted by 28 bits or with the pin select 1 SFR. So instead of specifying the hexa value of SFR, one can specify the bits of the SFR and mention the logical operators to set or clear the bits of the ports. Pin functionality of the LPC2148 as can be seen from the circuit diagram. Port 0.0 to port 0.31 is port 0 bits, that is 32 bits. Port 1 is available from port 1.16 to 1.31. To demonstrate GPIO, let us see the first example where a LED is connected to port 0.31, that is the last bit of port 0, which is connected in common anode configuration. And let us write a program to switch on or switch off this LED. So the example program for this is, if you refer the examples provided in ARM kit, you can see LPC2148 example codes. First example is Blinky. So in this example, as we have discussed, since we want the last bit of port 0, we want to set it. So you can say 1 left shifted by 31 bits and IO dir bit will be set with OR operation. And in the while loop, you can set the bit, delay, clear the bit and delay, and infinite loop. So if you compile the program, no errors, then you can go to project options for target. As said that it has to be 12 megahertz at present. The board is mounted with 12 megahertz crystal. Then we must select the internal ROM and RAM by default values. And then device is, yes, obviously LPC2148. Output, we want to create a hexa value. So you should tick this create hexa value and select the folder where this file is going to be saved. And then in debug option, we want to use the simulator. So select the simulator, then run to main program and load application at startup. So these both should be selected. So once you say OK, then compile the program, use the debugger to simulate the program. So in the peripherals window, we want to watch GPIO port 0. So that is this, which will show the bits of the port and their status. So if you now, it will start when we reset this thing. So it will start from the main program. Okay, now if you do the single stepping, as you can see now, so if you single step it, so IODIR, the first bit is set. Then if you again single step it, it will enter into the while loop. IO set bit. If I execute this instruction by single stepping, IO set in SFR, this bit will be set. Now it is a wait, is a loop. So in this function, we do not want to do single stepping. We want to complete this entire function in one step. So whenever there is a loop, you can step over the function. Okay, now it is executing. It's ready to execute the next instruction. Now again do the single stepping. As you can see, IO clear. So the bit is clear. Again, there is a wait function is there. You can step over so that that function will be executed in one shot. Now it is ready for the next instruction to be executed. And you can do now again step, that is single stepping. So this is how you can do the simulations of how one can configure the GPIO pins of the LPC2148 ARM processor, and then can set and clear the bits of the ports. Okay, so once the simulation is done, let us see how to download the program. You can use Flash Magic software. So first one should select the device. So we are using ARM-7. In ARM-7 LPC2148 is the device. COM1, computer serial port 1 we are using, standard baud rate, non-ISP. Operating speed of this board is now working on 12 megahertz. Erase blocks used by hexa file, you must select this. And then in advanced options, in hardware configuration, untick the DTR and RTS options. And once you connect the board, close the ISP jumper of the board and press the reset button. Now the board, ARM board, is ready for in-system programming. Now if you want to verify, go to the ISP, you can blank check the board. As you can see, it will read the board entire flash memory. Now it shows the status of various memory blocks, flash memory blocks, not blank, and some of them are blank memories. Similarly, you can see the security bits. Now it's saying that the CRP is disabled now. Similarly, you can read the device signature, that is the ID number of the your ARM processor. Right now, device ID is displayed here, and right now which bootloader is there in the LPC21xx is mentioned here. So this is exactly the device ID which is used by your microcontroller in the interrupt vector table. Then if you want to display the memory contents of the flash memory, then you can mention the memory block. So whatever is the contents of the ARM processor is displayed on the screen. Now if you want to erase the flash memory, then you can choose erase the flash memory. You can choose the options, what do you want to erase. Otherwise, by default we have already selected erase blocks to be used by hexa file. Now you can choose the file hexa file which you want to program the microcontroller, and you say start. Now it will erase the flash memory and it will do the programming. Once the program is finished, now on your board, that is on your LPC21xx board, there is a ISP jumper is there. Remove the jumper and press the reset button. So then the LED will start blinking as per your program. Okay. The next example is how to interface 16:2 LCD to ARM-7 microcontroller. As you can see in the circuit diagram, 16:2 LCD has a 16-pin connector where pin number 1 is ground, 2 is connected to 5 volts, and 3 is connected to ground by using a 1 kilo ohms resistor, which will control the contrast of the LCD. Pin number 15 is again 5 volts, 16 is ground, which will switch on the backlit yellow LED. About the interface, ARM-7 is connected with pin number 4 to pin number 14. First are the 3 control signals, that is pin number 4, pin number 5, pin number 6, which is RS read oblique write bar enable. On ARM-7 they are connected. RS is connected to port 0.2, read oblique write bar connected to 0.3, enable is connected to 0.4. Then about the data bus, DB0 to DB7, which is connected to port 1, that is port 1.16 to 1.23. So this is as far as a 16:2 LCD, how it is interfaced to ARM-7 processor. Now let us see how to write a program. Mainly these 3 control signals will decide whether you are sending data to the LCD or you are sending the control words to the LCD. Whenever you send the control word, this RS signal should be 0, and whenever you are sending the data, RS should be 1. A read oblique write bar is always low, so that whether it is a command or data, it has to be loaded into the control registers or the RAM space of the LCD. Then enable will enable the latch of the LCD. So RS is the one which decides whether you are sending data to the LCD or you are sending a command to the LCD. So what do you mean by data? Data means it is the ASCII values you will have to send so that LCD can display the characters on screen. Control words means control words are like initialization of the LCD for size of the character, blinking the cursor, clear the LCD, and so on, which are the standard commands. Now let us see how to write a program for initialization of the LCD and display the text on the LCD. So in your example folders, there is a test LCD program is there. So open the project. So in this, there is a main program, that is at.c, GSM at.c, where, as you can see, first, after specifying the target device, LCD initialization routine is called. Then few functions are written, which are there in LCD.c, which is a part of the your project group. So here, if you see the ports, how they are initialized, since RS is connected on port 0.2, so that is why the bits of the ports are specified here: RS, redouble, write bar, and enable. And similarly, since the control pins are connected on port 0, so the direction of the ports are set. DIOR is set as a output port 0.2, 0.3, and 0.4. And since the data bus is connected on port 1, so bit number 16, that is bit number 16 to 23, have to make it output. So bit number 16 to 23 is made as a output port. And since we are using GPIO, so in pin select 2, we have loaded all with 0, 0. So initially all the bits are set, control signals. Now we have to initialize the LCD. So how the LCD function works? In LCD initialization, as you can see, the control words like 0, 1, 38, 0F, 06, 0C. These are the control words where we'll initialize the LCD, like 8-bit mode, 2 rows, size of the font, display on, increment mode and shift, and clear the screen, and so on. So these are the control words. Whenever you are sending the control words, as you can see, we are using the command called LCD CMD function. So in LCD CMD function, what you can see is redouble write bar is low and RS is also low. So whenever RS is low, that means you are sending the command, and rest of the program is same, that we will make it low, then we will make it high, so that LCD will accept the command. So once the command initialization is done, then in the main program, once initialization, go to LOC. That means this, in the bracket, these two will specify the coordinates, that is a row and column. So first is about the row and second is the column. So in that will initialize, this is again a command which will specify the location of the text to be displayed on the screen. So whenever the position, if it is 1, that means you want to display on the first line. If it is 2, that means you want to display on the second line, that is second row. So first row address is 80 and last address of the first row is 8F. Second row is C0 address and last is CF. So that is how LCD RAM is identified by the line number, whether it is a 1 or 2. And column is specified by position. So once the LCD cursor is positioned, then we are using LCD write string command, so that whatever is mentioned in the codes will be converted into ASCII values, and it will call the function to write the data into the RAM space. So in the LCD write function, write string function, where, as you can see, now this time RS is high. So that is how now LCD will differentiate that whatever you are writing is not command, it is the data. So then the entire string, it will call this function to convert that string into ASCII values, and it will write it into the port, that is port 1. So then again we are calling go to LOC. Now this time it will select the second line and first column, and again we want to display the second string. So this is how you can use the LCD functions and write the main program, and then once the compilation is done, you can go to the flash magic, then the hexa file in test.underscore-lcd, there is 80.hex file is there, you can select it. Rest of the settings are same. Erase blocks used by hexa file, and you can close the jumper of your board, ISP jumper, and press the reset button, and then you can start downloading the program. So then first it will erase the flash memory and program the device. Once the program is finished, again you can remove this jumper and press the reset button. Then you will see that the LCD will display the text on the screen. So this is how one can write various one can use the functions of the LCD and display various text and the data on the LCD, which act as a monitor for most of the programs. The next example is about analog to digital converter, which is a inbuilt peripheral of ARM processor LPC2148. LPC2148 has two 10-bit A to D converters with 14 analog inputs with a conversion time of 2.44 microseconds per channel. So on the board, as you can see, the connector is provided to test the AD0, ADZ2, 3, which are connected on the connector pin. Let us write a program to read the analog input and the 10-bit value, convert into text form and display it on the LCD of this board. The example program for this is project, open project. Then third example, ADC and LCD project. So in the main program, apart from LCD initialization, first there is a to D converter initialization is there. So how to initialize the ADC? So there is another C file where there are two ADCs are there. In this example, we are using ADC0, where in pin select 1, where we want to left shift 25 times 3 and complement it and with pin select 1, and R1 by left shifting 24 times, so that ADC0 is selected not as a GPIO, it is selected as a analog input of channel number 1. So once the initialization of the ADC0 is done, then like in the previous program, LCD is initialized and it will display some data. Then we are calling this ADC function in turn, which will call this ADC read, where we are passing the channel number as well as the which ADC we are selecting. That routine is there in ADC.c, where we are calling this function. So in this function, first ADC0 control register, where will enable the channel and will start the conversion. So in ADC0 control register, from the data sheet, in page number 268, if you can refer ADC0 control register, which will in page 267, first which will select the channel, and then where, as you can see, the number of channels select bits, bit number 0 to 7 will select the channel. By default, it is channel number 1 will be selected. That is nothing but channel address. Then what is the operating speed of the A to D converter is decided by bit number 8 to 15. So maximum can be 4.5 megahertz is the operating speed. So that will be decided by the peripheral clock. Then do you want to operate the A to D in burst mode? Burst mode means repeated conversion. Then one can choose the burst cycles with what rate you want to have this repeated conversion, 4 clock cycles to 11 clock cycles, depending on the amount of resolution you want. And then one can start the conversion from analog to digital form. So like 001 will start the conversion. Otherwise, you can have a conditional start conversion by either interrupts or the external pins, which will trigger then allow to digital conversion. So that is the reason why we have selected the channel, we have specified the channel address, and then we are OR with that channel start address bit. So once the conversion is started, then in the do loop we are continuously reading AD0 GDR register, where in the data sheet the global data register is a 32-bit register. 0 to 5 is reserved. Then bit number 6 to 15 will consist of the data of 10-bit equivalent digital data for the corresponding analog signal. Then again 16 to 23 is reserved. 24 to 26 will represent the channel address, and if there any data is lost, if previous data has overwritten on the new data, overrun error will be set. Otherwise, we should continuously look for the done bit to select. That is bit number 31 will indicate whether the conversion is completed or not. So that is the reason in the program we are continuously verifying whether bit number 31 is set or not, so that till the end of conversion is there, it is in the do loop. Once the conversion is completed, then we are reading the data register, D0 register, and then that I value we have right shifted by 6 bits and with 03FF, so that in the GDR register the result is there from bit number 6 to 15. So we'll have to right shift by 6 bits so that the data will be available from D0 to D10. And then we want to mask the unwanted bits by ANDing 03FF, so that the data is available of 10 bit. So the same thing will be repeated if instead of choosing ADC 0, if you choose ADC 1, the same procedure is adopted, except that this time the control register is AD1CR and the data register is AD1GDR register. So that is how the ADC read will select the channel and will select the A to D converter. Once the conversion is completed, the value will be returned to ADC value, and by using this LCD port string, we are displaying that contents on the LCD by specifying the line number and the characters to be displayed, the buffer characters to be displayed on the LCD. So once you compile the program, let us simulate the program. After compiling, go to debug. As you can see, since we have used A to D converter 0, all the peripherals, the peripheral SFRs are shown here. The channel data, GDR, and the control register, and the control bits are indicated here. So initially, if you see the analog input also, we can give reference voltage is 3.3 volts. So to AD0, if we are giving 0 0, and if we run the program, then the data register consists of 0 0 value. Now if I slightly give some voltage, and if I run the program again, and if I stop it, first run the program by using single stepping or step over. Then you can run the whole program in one shot and make the changes in the analog input voltage. And if you stop it, then you will see the change in equivalent hexa value. And also you can see the done bit is set, where that indicates the conversion is completed, and it has overwritten because we didn't read the every sample. Similarly, if I increase the voltage to 3 and if I run it, and if you stop it, now this is updated equivalent hexa value for a corresponding analog input. So that is how you can simulate the program. And similarly, you can also load the program on the board. First close the ISP jumper, press the reset button, select the code, then start. If there is any reset problem, press the reset button. Now it will erase the flash memory and program it. Once it is finished, remove the jumper and press the reset button. You will notice the LCD will display the corresponding BCD number for a given analog input. So this is how you can vary the voltage on this pin of channel number 1 of A to D converter, where you can give the voltage anywhere between 0 to 3.3 and verify whether it is equivalent analog voltage is displayed on LCD or not. Now let us see the next peripheral of LPC2148 ARM processor, that is digital to analog converter. The LPC2148 has a 10-bit digital to analog converter where the output is available on GPIO pin, A out pin. You need to program the pin select 1 register of bit number 18 and 19 to make that pin as a analog output pin. The control register for the digital to analog converter is DACR, which is a 32-bit register. Out of that, the bit number 6 to 15 represent the digital value which will be converted into analog form, and there is a bias bit which will decide the output current. For example, if it is set to 1, the conversion time is 2.5 microseconds and the driving current is 700 microamperes. But if the bias bit is 0, then the conversion time is lesser, 1 microseconds, but the driving current is less, that is 350 microamperes. The DACR control register bit number 6 to 15 represents the binary value which is converted into analog form and available at A-out pin, and bit number 16 is the bias bit. So let us see how to write a program for digital to analog converter. So the example is project, open project. In LPC2148 example codes, fourth example DAC. So in this program, the pin select register bit number 19 is set by 1 in order to make it DAC as a analog output. Then the remaining program is same, which is a LCD initialization, just to indicate the status of the output. Then one function is written to generate a sine wave. The first part is to generate half wave and second part is to generate the full wave, where a frequency term is mentioned and the amplitude is mentioned, and the sine mathematical function, which is a inbuilt function of the math library, is included. So the values which are generated will be stored in the buffer wave as a buffer. Then in the loop, the contents of that buffer is left shifted by 8 bits. The reason to left shift by 8 bits is 6 times we need to shift. That is because the data is available in the DAC register from bit number 6 to 15. So 6 times you have to shift, and 2 more times we have shifted, so that the amplitude is multiplied by 2, so that the amplitude will be increased. So this value will be stored in DACR register, which in turn will convert into equivalent analog form. So first compile the program, then debug the program. As you can see, the peripheral this time we would like to see digital to analog converter. So let us execute the program by single stepping. So let us use this step over function to execute various functions, which is in real time. Okay, then LCD clear. Okay, now it will enter into the function where the sine wave is calculated. So this will be in the loop. Now this time I want to come out of the loop. So let us use step out function. As you can see, now this entire function is getting executed. You can see in the peripheral of D2A converter, DACR control register contents are, that is bit number D6 to D15 are continuously modifying, and you can also see the analog output of the DAC, which shows that the sine wave values are converted into equivalent analog voltage. So this shows the simulation of digital to analog converter. Now stop the simulation. Now in order to program this, use the Flash Magic software. In LPC2148 example codes, fourth example DAC 80.hex file. Close the jumper, ISP jumper on the board. Press the reset button. Start loading the program. So once the program is downloaded, now it is finished, you can remove the ISP jumper, press the reset button and connect the CRO probe on A out pin, that is P0.25. On pin number 1 with reference to ground, then you will see a sine wave is displayed on the CRO. So this is how one can verify generation of various waveforms by using digital to analog converter of the ARM processor. The next example is about read the data from the A to D converter and write the data to D to A converter in a closed loop. So the project is fifth example ADC DAC LCD. In this example, first DAC pin is selected by writing 19th bit as a 1 and 18th bit as a 0. Then similar to previous program, ADC is initialized, LCD is initialized. Only difference is whatever is the data we are reading from the ADC, left shifted by 6 bits, right to the DACR control register, and it's in a while loop. So you will notice whatever is the input is given to the ADC channel number 1 will be written to DACR control register. The value will be displayed on LCD as well as it will out to the digital to analog converter. So compile the program, debug the program. As you can see, we'd like to view ADC peripheral as well as DAC peripheral. You can do single stepping, or you can execute in one shot, run the whole program. So when the program is continuously running, you can give the voltage to the ADC. Then you can enable the interrupt so that the ADC will convert equivalent analog voltage into digital form, and done bit is set. Now as you can notice, the same value is written, that is 4D80. This value is written to the DACR control register of D to A converter, and equivalent analog output voltage is generated 0.999990. So this is how you can forcefully change the voltage in the simulation itself, and then see the corresponding output at the DAC by set or clear the interrupt pin of the microcontroller. So once you do the simulations, you can go to the Flash Magic software, and fifth example, can load the hexa value. Once the programming is done, then on your board, on pin number 1 of the ADC, that is ADC 0.1 first channel, give either 0 volts or 3.3 volts on this pin, and then monitor on pin number 1 of DAC the corresponding analog output voltage either on CRO or on multimeter. So this is how you can verify analog to digital converter and digital to analog converter in a closed loop fashion.